In this video, we will chat and learn how to use the chain rule, and you will also learn when to use the chain rule. So this follows in the footsteps of function operations from previous math courses when you learn how to add, subtract, multiply, and divide two functions. So usually what you will see is something like this, say f plus g of x, or f g of x, where you learn how to add, subtract, multiply, and divide as stated. The usual next step is to learn how to compose two functions, where you say f compose g of x or f of g of x. And we talk about how to find the domains of these functions, and it's a blast. But in this unit, you've seen how to find the derivatives in all of these scenarios by using the sum and difference rules and the product and quotient rules. Next up, how to find the derivative of a composition of functions. It will be of the utmost importance to recognize when a composition of functions is presented. That is, you should be able to identify an inside and outside function. For the following examples, we will just identify which function is on the inside and which function is on the outside. So when we look at these examples, especially if we start for number 1, you can see that here, that this expression 5x squared minus 3x is on the inside of the sine trig function. So here for the sine, we will say this is on the outside. And so what this allows us to do when we start actually looking at the chain rule is it will allow us to actually find this derivative pretty simply. And by doing that, we will want to set the inside equal to u. So 5x squared minus 3x. And what we will have on the outside then is the sine of u. And this makes sense, and this is how I'm going to explain the rest of these three examples down here, is that if you make this substitution for u, that is, if you put this in here, you'll end up with what you started with over here, sine of 5x squared minus 3x. All right, so there's the inside and the outside. We set the inside function equal to u. All right, not bad. So in this next problem, you can see here that the inside is x squared minus 6x minus 16. So I'll call that the inside, and then the outside in this case is that power to the power of 100. So here the inside is u equals x squared minus 6x minus 16, and the outside will be u to the 100 power. And again, if you substitute in this expression for u, you'll end up with what we started with. So we're just decomposing the composition. Here in the third example, you can see that there's clearly an x inside the secant function. However, this power 4 right here tells us that we should rewrite what this function looks like. And so this function, the 4, is affecting the secant, not the x. So we need to rewrite this as secant of x raised to the 4th power. So now you can see that the secant of x is what's on the inside and not the actual x as we thought originally. And on the outside is the exponent 4. So here we will have the inside u equaling the secant of x, and the outside would be u to the 4th power. Pretty similar to this one over here, but the exponent in this case is hidden right after the secant, and that is what ends up being the outside function. And for this last one here, we have p of x equals the fourth root of x minus 5x cubed. And that, again, to see this easier, should be rewritten as x minus 5x cubed to the 1/4 power. Similarly to how the square root turns into a 1/2, the fourth root turns into a 1/4 power. So now this is much easier to see that this is what is on the inside, and then this 1/4 power is what is on the outside. So again, over here to the right, I'm going to write that the inside is u equals x minus 5x cubed, and that the outside would be u to the 1/4 power. So one other thing I want to say about this very quickly is that usually you can look for a set of grouping symbols like parentheses. In the rewrite, you still have parentheses, or inside of a trig function or inside of a radical sign to find out what the inside function will be. And you can notice that every inside function here is set equal to u. There we go. And every outside function has u instead of x's. And that if you make the substitution for this u in the outside function, you'll get what you started with. So if you substitute this whole expression in for u, you get what you started with. If you substitute this expression in for u, you get what you started with. If you substitute this expression in for u, I think you guys get the idea. Let's go on to what the chain rule actually states. On this slide, as promised, we have the chain rule and how it is stated as a theorem, and this can be represented many different ways, or a few ways anyway. So here it is. If y equals f of u is a differentiable function of u, and u equals g of x is a differentiable function of x, then y equals f of g of x, and here are the statements of the chain rule. So we have y prime equals f prime of u times u prime, which equals f prime of g of x times g prime of x. Or, and this is how I'm going to think about it down here, is that we have dy dx equals dy du times du dx. So in order to explain this a little more, is that if we take the derivative of y with respect to x, we can use the idea from the previous examples on the last slide, that we can take the derivative of y with respect to u, and that's taking the derivative of the outside function with respect to u, and then to that we can multiply the derivative of u with respect to x. And in fact, remember, we set the inside function equal to u, so this would be the derivative of the inside function with respect to x, and that's how I'm going to work through the rest of the examples. Let's take a look at a few examples. So here you can see that the first example is f of x equals secant x to the 4th power. And our direction is to differentiate and simplify. So the first thing I want to do is identify what are the inside and outside functions, just like you've had some practice with this already. So I know that here the inside function will be u equals x to the 4th power, and the outside function, which I'm now going to call y, equals the secant of u. Because remember, when we have this dy dx equals dy du times du dx. This is the derivative of y with respect to u. So we have to have a y in terms of u. And then we will multiply the derivative of u with respect to x. That means u has to be a function of x. So we can do this. Let's take the derivative of y with respect to u. So the derivative of secant u will be secant u tangent u. And to that, we're going to multiply the derivative of u with respect to x. So what's the derivative of u with respect to x? Well, if we just take the derivative of this side over here, that is 4x cubed. So this will be times 4x cubed. So now we have this equaling f prime of x, right? The derivative of f of x. And now you can see over here we have an issue. We have secant and tangent in terms of u, but everything else is already in terms of x. We need this in terms of x because we have f prime of x, not f prime of u. So in order to fix that, we will go back and substitute this x to the fourth power back in for u. So this will be secant of x to the fourth power tangent of x to the fourth power times 4x cubed. And this is a final answer. If you like simplifying it like this, saying 4x cubed times secant of x to the fourth times tangent of x to the fourth, just to see the 4x cubed in the front, that's fine. So either of these are good answers, and that's as simplified as they can get. In the next example, you can see here we have g of x equals cotangent x squared minus 6x plus 9. So again, what we want to do is identify what's on the inside. And there it is. This will be what's on the inside. So the inside is u equals x squared minus 6x plus 9. And on the outside, we have y equals cotangent of u. So if you substitute this back in for u, you end up with what we started with. And g of x and y are the same thing. So we can now, looking back up here, we can find the derivative of y with respect to u. So we can just take the derivative of this just fine. That leaves me with, let's see, so that leaves me with negative cosecant squared u. And to that, again, looking up here, we're going to multiply the derivative of u with respect to x. So if we take the derivative of this function over here, we will end up getting 2x minus 6. But again, this is equal to g prime of x. We can't have any u's over here, so we have to make this substitution in for u. So u will turn into x squared minus 6x plus 9. So our final answer will look something like this. Negative cosecant squared of x squared minus 6x plus 9 times 2x minus 6. And I guess I spoke too soon. This is not a final answer. Notice that you can common factor a 2 from this factor back here. So we'll do that and push it to the front to get a negative 2 cosecant squared x squared minus 6x plus 9 times x minus 3. And again, if you want to push this x minus 3 to the front, behind them negative 2, that's fine. It's fine where it is back here. So let me box that in. This is the final simplified answer for the derivative of this composition of functions. For these next two examples, we will need to differentiate and simplify again. So let's take a look at what happens here. Especially with this first one, since we have that square root, I'm going to rewrite it as d dx, the derivative with respect to x of cosine of 3x raised to the 1/2 power. So now this is much easier to identify what is on the inside and what is on the outside. Okay, so we can, take the, set these equal to little functions over here. So the inside is u equals cosine of 3x, and y is equal to, this is the outside, y is equal to u to the 1/2 power. So again, we can say that the derivative of all of this will equal 1/2 u to the negative 1/2 power times so I took the derivative of this function with respect to u, and then we're going to multiply the derivative of this thing with respect to x, times the derivative of cosine of 3x. So, oh no, look at this. This has an outside function, and this has an inside function. So we have to do another chain rule. Oh man, here we go. Let's see if we can do this expediently. So what's the derivative of cosine? That is negative sine of 3x. And what's the derivative of what's on the inside? That is just 3. Wow, so we had to do a little bit of extra work here. There was a chain rule inside of a chain rule. So we had three derivatives we were taking. So let's do some rewriting here. This can't be u, this needs to be in terms of x. So we can rewrite 1/2. And since this has a negative exponent, I'm going to push all this to the bottom. So instead of writing u, I'm going to write cosine of 3x, that whole thing raised to the 1/2 power, times negative sine 3x times 3. And so to write that more simply, I can write negative 3 sine 3x all over 2 cosine of 3x all raised to the 1/2 power. So you can see we had to think of another outside-inside situation over here while we were trying to think of an outside-inside situation. So the idea here is just to practice, and make sure you understand what's going on with these double chain rules. All right, so we have this example done. That's as simple as it gets. We can't really do anything with this without getting into some ridiculous exponents over here. Not something I want to work with or bother you guys about. So in this next example, you can see we have y equals this expression times this expression. So this right here tells me there's going to be a product rule. And we may have to continue this on the next slide. So I know here's the first function, or the first part, and here's the second part. So I'm just going to write out the product rule as normal. So I say y prime equals the first times the derivative of the second which is the secant of negative 2x, plus the second, the secant of negative 2x, times the derivative of the first, which is x squared plus 3x plus 6 raised to the 16 power. So this is what the product rule looks like, if you'll remember. And what you'll notice is that this part here, that's not so bad, there's no derivative. This part here, secant negative 2x, no derivative. But these two parts, we need to find the derivative. And for each of these, we will have to use the chain rule. So you can see that this is on the inside and that this is on the outside. And again over here, that this is on the inside and that this is on the outside. So you will have to use u equals negative 2x for this derivative here, and you'll have to use u equals x squared plus 3x plus 6 for this derivative here on the inside. Over here, the outside is y equals secant negative 2x. Oh, not negative 2x. It's y equals secant of u. There we go. And in this derivative over here, it will be y equals u to the 16th power. This will be continued on the next slide. So from the previous slide, we have all of this information, the last line and the u's and the y's for each chain rule derivative here. So what we have to do now is actually go through and take these derivatives using the chain rule. So we end up with y prime equals, we have x squared plus 3x plus 6 to the 16th power times the derivative of secant u, right? We have to take the derivative of y with respect to u. So that is the derivative of secant u is secant u tangent u. And then the derivative of u with respect to x is times negative 2. Plus, we will have secant of negative 2x times, we have to use the chain rule for this derivative now. So the derivative of y with respect to u over here is u to the 15th power. So u to the it is 16u to the 15th power times the derivative of u with respect to x will be 2x plus 3. That's not so bad, but we have to go back and substitute the correct u's where they're supposed to go in the respective chain rule derivatives. So this will equal x squared plus 3x plus 6 to the 16th times the secant of negative 2x times the tangent of negative 2x times negative 2 plus the secant of negative 2x times 16 times x squared plus 3x plus 6, 15 to the 15th power times 2x minus 3, plus 3. So now, since this expression is very long, I would like to be able to see if I can simplify this in any way, as it is part of the directions. So what we can do is we can common factor some of these out of each term. We can common factor one of these out of each term. And in fact, we can even common factor a negative 2 out of each term, just to make it worthwhile. And I think that's it. Here we can common factor x squared plus 3x plus 6. We can common factor 15 of those out. Because we have 15 in this term and 16 in this term, you can only take out the minimum number. So there that is. We can common factor a secant of negative 2x out from each term. And like I said, we can common factor a negative 2. And I'm going to put that right up front. So this negative 2 is gone. When you divide 16 by negative 2, you end up with a negative 8. The secant negative 2x is gone from both of those, and we're left with 1 here, and all of these are gone. So let's see what that leaves us with on the inside. On the inside, we've got, let's see, x squared plus 3x plus 6 times the tangent of negative 2x minus, and that's because of the adding a negative here, so minus 8 times negative, no, not negative, times 2x plus 3. And that's it. That's as simple as we can get, but I'd rather deal with two terms that look quote unquote simpler than these two terms. So this here will be your final answer for the derivative of the second exercise we started on the previous slide. There are two more examples, and on this slide you can see one of them here. The directions are to differentiate and simplify. So here we have f of x equals the square root of the rational expression 3x plus 5 over x squared minus 2. X squared plus 2. So the first thing we want to do here is rewrite it so that this looks like 3x plus 5 over x squared plus 2. Squared plus 2, there we go, to the 1/2 power. Then we can identify what is on the inside of the function. So the inside will be u equals 3x plus 5 over x squared plus 2. And the outside is easily identifiable now as the exponent 1/2. So we'll say the out is y equals u to the 1/2 power. So now if we're trying to find the derivative, f prime of x equals the derivative of y with respect to u. So that will end up being 1/2 u to the negative 1/2 power times the derivative of u with respect to x. And you can see here that because of this quotient, we will need to use the quotient rule to figure out what that derivative is. So we will use the denominator, x squared plus 2, times the derivative of the numerator, which is 3x plus 5, minus the numerator, 3x plus 5, times the derivative of the denominator, x squared plus 2, all over the denominator squared, so x squared plus 2 squared. This expression here, we've almost found all of the derivative except for these little parts here. And we need to go back and substitute this quotient in for this expression. So, and at the same time, I'm going to push this u to the negative 1/2 power to the bottom of this fraction. and change the exponent to a positive. So there's going to be a lot happening here. So this will be 1 over 2 times the fraction 3x plus 5 all over x squared plus 2 times x squared plus 2 times the derivative of 3x plus 5 is just 3 minus 3x plus 5. The derivative of x squared plus 2 is 2x all over x squared plus 2 to the second power. And I just realized over here in the first fraction that this is 1/2 power. So make sure you're not forgetting the 1/2 power in the denominator of this first fraction. So now there's a lot of simplifying that needs to happen here before we get to our final answer. The first of which is to multiply all of this stuff out and combine like terms in the numerator of this fraction. The other thing that we need to do is multiply by the reciprocal of this fraction, right? We don't want fractions within fractions. So this side, this fraction, can be rewritten as x squared plus 2 to the 1/2 over 2 times 3x plus 5 to the 1/2 power. When you look at this next fraction and distribute the 3 here and here and the 2x here and here, we end up with the following fraction. 3x squared plus 6 minus 6x squared minus 10. This should be a minus 10 right here, or minus 10x. So then I guess there's just a couple more things that we need to do, and that is to simplify whatever is in this set of parentheses here. And it looks like we have an x squared plus 2 to the 1/2 and an x squared plus 2 to the second power, and we can reduce away half a factor here. So this would be 3/2 left over down here. And I think that when you simplify this over here, it ends up being negative 3x squared minus 10x minus 6. And it looks like our plus 6. And that's fine. It doesn't look like that factors at all. So now we can just rewrite this entire fraction as the following. So since we reduced this entire term here, or this entire factor here, over here with this denominator, that whole factor is gone, just leaving us with this in the numerator. So negative 3x squared minus 10x plus 6. And then in the denominator, we have the 2 times 3x plus 5 to the 1/2 times x squared plus 2 to the 3/2. So this here will be the final simplified answer of the derivative of the function we started with up here. One final example, we have y equals the cotangent of sine of t over t. And with this example, again, we will want to set up an inside and outside function. So the inside is here. So I'm going to say inside equals u, which is sine of t over t. And the outside function is here, y equals cotangent of u. That being said, now we can take the derivative of y with respect to u. So the derivative of cotangent, so let's start y prime equals the derivative of cotangent of u is negative cosecant squared of u. And to that we will multiply the derivative of u with respect to t this time. Since we're using the variable t here, we will use du dt instead of du dx. So the derivative of sine of t over t will require us to use the quotient rule. So we will start with the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared. And again, since we started with t's, we need to change this u over in terms of t. Well, that's pretty easy. We just substitute that in. So we will have y prime equals negative cosecant squared of sine of t over t times this whole first term here, t sine of t turns into t cosine of t, minus this entire second term here, the derivative of t is 1 times sine of t is sine of t, all over t squared. So I believe that's it. We can't really simplify anything here. We can't common factor anything. It's this entire fraction times this cosecant squared. There's nothing else to do here to simplify this, so here we go. This is the final answer for the final simplified derivative for the original function cotangent of sine of t over t.